down payment on a Falcon 9 launch vehicle. Our contract has a launch window as early as December of 2013 and as late as the middle of 2014. On the left, you see the picture of our stack-up. We are a single-stage mission to the moon. There are no star motors anywhere in our architecture. The Falcon 9 throws us into a TLI, and then our vehicle breaks into lunar orbit and then descends to the lunar surface. And as part of the ILDD, the Innovative Lunar Demonstrations Data Program, we have a first task order to actually build the structure for the lander, which is on display over in the tent. You can go up and see it. This structure was recently put on a shake table, and we discovered that it is in fact stiff enough to resist the stress of launch. And you can see that some gold boxes there. Those represent both payload locations and boxes for other parts of our components. So for your payloads that we'd like to take to the moon, most of them probably would mount on the underside of that main deck. So far we have about $11 million in NASA contracts, ILDD plus SBIRs for ice mining and gravity offload. And we have been able to get a pretty fast start by using the Carnegie Mellon facilities and the talent there. Okay, you can do it. There we go. So one great thing about Pittsburgh is we have slag heaps from abandoned steel mills that look very lunar-like. Absolutely. It's a fairly large robot. It has a camera head on the top that can turn 180 degrees. It has a hot side where the solar panels are located and a cold side for the radiator. So basically it operates by keeping the solar cells always towards the sun and the radiator always towards black sky. Because the camera head can rotate, it can go forward or away from the sun equally well. And its suspension is built such that it can go over pretty extreme terrain and still keep all four wheels on the surface. We are unlike the Mars rovers. The Mars rovers have their actuators actually in the wheel hubs, which works for Mars but wouldn't work on the moon because of the lunar dust and because of the temperature extremes. It gets sort of to a low oven temperature during the day, and so there's no way you could put a radiator down by the wheel to keep that motor cool. So instead, we have all of our two actuators in the body of the robot, and we use bicycle chains essentially to drive the wheels. And that's very robust because if you think about a chainsaw, a chain can go through a lot of rough experience and still keep on working. Also, a great thing about Pittsburgh is we have great machine shop capabilities. This is the deck for the lunar lander being hollowed out at Edgar Industries. Those four cutouts are for the four propellant tanks. This is the deck being offloaded at Carnegie Mellon's Planetary Robotics Laboratory and being fitted onto one of the two cones that form the main structure. A cone going down to the launch vehicle and a cone going up that holds the robot. And as I said, this primary structure is on display over in the tent. As you can see the sun going down, the folks putting this together worked very, very long hours to get it ready for the shake table test. Okay, we have a number of locations that we could attempt as our first mission. You see the lander flying over one of the lunar skylights. That's supposed to be the Marius Hill skylight down into the lava tubes. We've put in a proposal to the Office of Chief Technologist for one of their technology demonstration missions where we would fly directly over the hole using our landing sensors to begin mapping the hole, land about 50 to 100 meters away, and then our robot would roll off and scout around the edge and build a good 3D model of the hole from all angles. We have phase 2 SBIR for an ice mining robot that would go to one of the poles in the partially illuminated regions, not the permanently shadowed regions, and be able to take off the top layer of dry soil and then get access to the water-containing soil underneath. And finally, we would dearly love to go back to one of the Apollo sites. As you know, NASA has a lot of interest in how space weathering has affected the various materials there. And we think for the public, it's one of the few places on the moon that they can identify with, a location to go look at. We think that the guidelines that NASA's come up with for visiting Apollo sites are pretty reasonable, with good keep-aways for Apollo 11 and Apollo 17, but the ability to roll up very close to the instruments on the other sites and get some close-up looks at them. Can all get what they need from one of our missions without having to be the only bill payer to get them accomplished. And we believe that we'll be able to have a fair amount of commercial revenue from the HD 3D video. If you've ever put on the red-blue glasses and looked at some of the Apollo era still photos that the astronauts took by clicking their Hasselblad and stepping to the left and taking another picture, you get a completely different sense of depth on the moon from those 3D still photos. So we'll do video in 3D, and I think that will really open people's eyes to what exploring and having a frontier on the moon could be like. We also are unlike the other teams that have gone after the Google Lunar X Prize. There were two equally rational paths to take. One is build something small that is just sufficient to win the X Prize under the X Prize rules, so they can get the smallest possible launch vehicle and therefore the lowest cost. We took the other path, which is to build something fairly large that can carry a lot of payload, 110 kilograms, and that therefore we can use again in additional missions to carry payload for customers. So we believe that we won't have to start over on mission number 2. We'll already have the basic hardware and basic design that is robust enough to do a lot of things for the people who want access to the moon. And not only a commercial fixed price culture, but coming out of Carnegie Mellon's academic culture, university folks are poor, and they put $1 on the rack and make it scream just to get enough Buck Rogers for their bucks. So we can do this with a very good fixed price culture. For the decadal survey, there was a study done of how much it would cost to take 50 kilograms to the South Pole to do ISRU. And the answer they came up with is about $150 million to develop the instruments, and then another $700 million for the launch vehicle, the spacecraft to get it there, the rover to provide mobility, and then the staff costs to make all that possible. The astrobotic alternative, NASA pays itself the same $150 million to develop instruments, but at our $2 million per kilogram price, those 50 kilos only cost $100 million to get to the surface instead of 700. So we believe that by shifting to a commercial paradigm, NASA and the researchers that it supports can get done what they want to get done for about 1/3 of the traditional cost. As I said, on the rover, it's $2 million per kilo. On the lander, if you don't need mobility, it's 1.8. We supply power and we supply communications. In most cases, we also provide good thermal control. If you want to be on the rover and have access to the environment, then you'd be on the back shelf of the rover, and that would not have thermal control. But if you're on the lander and you're mounted underneath that main deck plate, like the gold box is shown, you'd use that deck plate to radiate away your excess heat. That gold box is just an example. The teal box you see there is an indication of the payload envelope. People won't be stuck into a box, but that's the envelope you have to put your payloads on, and they can extend fairly down towards the soil, so that the bottom part of your payload may be only 25 centimeters off the deck, and has very easy access to the regolith. That payload envelope extends out beyond the deck, so you also have visibility to the sky. So, how can you buy from Astrobotic? NASA Salmon Calls, we believe that those will be cranked up to allow individual researchers to say, I've got 5 kilos, I want to get to the moon, and you can compete based on your science, and then you just buy a service from us. OCT has a number of programs that are funding tech development that might also have a science component. Or if you've got foundation or corporate funding, you can come directly and just do a deal without needing a lot of intergovernmental agreements to get it accomplished. So that's my talk, and I'm eager to answer your questions.
Thank you. Any questions?
There's one in the back. Oh, by the way, over at the tent we have our payload users guide. They're going fast, but if they're out when you get there, you can download it from our website.
Can you just tell the 1.8 or 2 million per kilogram for an instrument, does it include data back to the ground?
Yes, it does. It includes comm back to the ground.
Any further questions?
I think you had your hand up.
I had a very simple question. How does the rover get out of the lander? Because I went over and inspected that beautiful model, but I don't understand how. It looks like it's an inverted triangle, but does it pop out like this?
Well,
It's kind of cool.
these are the ramps. The ramps are the only things that are stowed when we launch. When we launch, the legs are already down, but after we land, then those ramps would deploy and they would roll down. There are ramps on the front and the back, so in case one of the two areas is not good, we can roll off the other way.
And it's not like in the typical Mars rover bubble thing. You bounce around.
No airbags will die during this process.